Hokie dokie. In this video, we're going to be working through 1026 Lab 3. It's a pretty quick one, to be honest. Let's get started. So a lot of it, we can probably just look at this, and then we'll get into the Excel stuff. So let's get into it. So building a model. We're talking about infectious diseases and spreading and yada yada. There's some assumptions. Yeah, don't need to worry about that. Let's start with a simple example. So where each sick person infects 5 new people every single day. So at time 0, the first patient gets sick. So n at 0 equals 1. So n is the number of people sick. That is 1 at day 0, at the very start. This person begins to infect other people at a rate of 5 new infections per day. So it spreads rapidly as each infected person infects 5 new people every day. With that in mind, fill in the blanks below. So if there's 1 infected person, they will infect 5 new people a day. If there's 2, they're gonna infect 10 people a day. So it's always that the number of infected people times 5, right? So 2 times 5 is 10. 5 times 5 would be 25. 100 times 5, 500. N times 5, 5n, right? So then they're saying basically what we just derived is like the rate of change. And so they say dn over dt is the change in sick people over change in time. So it's the rate at which the total number of infected people is changing per day. And so dn over dt is the rate at which the disease is spreading. So right here, again, it's the same thing that they have right here. This would just have 5n new people infected per day. You've just developed a differential equation to model the spread of our sample disease. So dn over dt, again, would just be 5n. And because they say initially 1 person infected at time 0, this would be 1 for n of 0. Look at the formula. As time goes on, will the disease spread at a constant rate, or will it spread faster or slower? So when we look at the formula, 5 times n, they ask, will the disease spread at a constant rate, or will the disease spread faster or slower? So a constant rate would mean that the rate of change is a constant. So to be a constant just means to be a number. But if it's 5 times n, then at one point it might be 5, at one point it might be 10, at one point it might be 25. So that rate of change is changing. And so that rate of change is not constant. So it'll begin to spread spread faster as the number of sick people n increases. And we decided that because the rate is 5n. And so it's just going to go up as n goes up. All right. Then they said, just a different example, but like very similar. What if each infected person infects 10 new people per day and 6 are initially infected? So if in the previous example it was like 5 new people a day, like per person, then in this one it's 10, so this rate of change here would be 10n. And if it's 6 initial people, then it would be n of 0 equals 6. In general, what if each infected person infects A new people per day and C people are initially infected? Well, applying what we just did here, if it was 10n here, then in general, if it's A new people per day, then it would be A times n. And then C would be the initial amount of infected people for n of 0. So n of 0 would equal C. dn over dt is A times n. And they give all those to us right here. So A times n, C. And then they say, like, with a differential equation, dn over dt, and with this initial condition, we can solve for what we get from that is this exponential growth equation, which is used to, model situations like this. I'm gonna skip through this. All right. So then they ask, like, how we would input this function, this CE to the AT in Excel. So we'll talk about that as we get going, but it'll basically be C times EXP, and then in parentheses A times T, and then close parentheses. So visualizing the model, Let's see. Okay. All right, so here's where we actually get into Excel. Looking at these first two columns here, just the first two, they tell us to label T and N1. Let me see if I can view all of this. There we go. So we put 0 to 10 right here, and then they give us a function. So they say A is 0.6 and C is 5, so we're just inputting those A and C values accordingly. So let me make sure I did that right. So looking up here, we can see that the C value of 5 goes in front. So we have 5 times E, but E is EXP. So EXP is the function for E to some power. And then in parentheses, you put what's in the exponent. So A times T would be 0.6 times T, which anywhere you see T, you're just clicking on A2 or typing A2, right? So you hit enter and you're able to drag this corner down to fill in those values. And then they ask you to create a little scatter plot. So this is the one for the first column. Again, you can click and highlight A and B like that, and then insert scatter like that, and click on that first one, and that's what you get this from. So that graph is definitely increasing, right? Increasing. It's going up from left to right, and they talk about concavity. It would be concave up, because concave up is like the upward shape U curve, like it ramps up. So that has that concave up behavior. All right. So then they have us try a few different C and, or actually no, we keep C the same, but they have us try a few different A values, right? So let me just kind of like show you what they do. So you can see in this equation here, the A value is 0.6, and they make you do an N2 where the A value is 0.9, and then an N3 where the A value is 0.3. And so basically just change the equation, make sure you're still referencing A2 anywhere you see T, right? And then you'll drag these equations down, and just to kind of get a glimpse, I don't think they really tell you to do this in the lab, but I graphed individually N1, N2, and N3 down here, so we get a glimpse at, you know, what kind of Y values we have. You could also just see it in the columns here, but I like the visuals. So the question is, what's the difference, right? So the idea is the smaller the A value, the less drastic the changes and the less drastic the Y values you're getting. In other words, like the less amount of people that are being infected, right? So the smaller the A value, the less people being infected. And then we look at N2, which had the higher 0.9 A value, and you know, you can see how drastically that eventually goes up into the 40,000s, which is crazy. So the higher the A value, larger the A value makes the graph blow up to higher values, and then the smaller the A value makes the graph, just kind of ramp up, not as drastically, to smaller function values. Something like that. So now experimental data. So now we're looking at the data from the first set here. So the first thing they ask you to do, I'll kind of just like do this again. The first thing it asks you to do is to highlight all of this stuff, and then insert a scatter plot. And I'm going to redo it because I don't know, I was worried this one might not be right. I'll show you what I mean in a second. I had some error when I was doing this before. Anyway, so we get this data, and what do they ask about it? They say, why do we start with C equals 8? That's a good question. I don't know. Why do we start with C equals 8? So C equals 8, you can see C equals 8 is like the starting value, I guess. I don't know. It's a weird question to ask. The best way I can answer it would be C equals 8 is C equals 8 because the number of initially infected people in this situation was 8. That's probably the best I have. I don't know. So 8 people were maybe initially infected, and then it eventually started to spread. So that's why, that would be that. Why do we need to change the value of C? I have no idea. I mean, maybe that might make it blow up too fast? These are weird questions, I'll be honest. I don't think I understand the full scope of these. They kind of just I don't know. I'm gonna leave it at that. I'm sorry, I'm not an expert in trying to understand what they wanted of you there. We're gonna just keep going through it. Data scientists who analyze data, try to fit curves, yada yada. So anyway, they've come up with this function here that is meant to best match this data here, right? And you can see that the C value in this equation, at least, is much smaller than 8. It's 0.705. So maybe that had something to do with it. Maybe we needed to change the value of C. It needed to be smaller. Otherwise, we wouldn't have been able to like approximate, like to fit a curve that best fit this data accurately. I don't know, something like that. It feels like the question is out of order. This whole why do we need to change the value of C? I don't know. It feels wrongly placed, in my opinion. I don't know. So, anyway, let me stop rambling. They ask you to use that formula, the one they came up with, to put t values in this column, so 0 to like 250 or something initially, and then input this formula here. So I'll kind of do the side by side. Looking at this equation up here, we can compare it to 0.705 exp 0.032 times d2, right? We hit enter, and we can drag this formula down. We do our clicking on the corner, drag it down, and we just drag it all the way down to 250 like they ask. Those values should be solid, so at 200 days there will be so many people. At 250 days there will be so many people. So let's see if I can find them real quick. 200 days, looking at like 424. 250, we're looking at like 2101. And then they ask something about, so they say Liberia is about 4 million people. And so if we extended these values, when would hypothetically the disease infect everyone, all 4 million people in Liberia? So we extend these values. Again, you can like whatever the last data point you have is, you can always like highlight those columns and just like drag it down, right? So anyway, we drag it down and we get to a point where at was this time? Yeah, so like 485 to 486, you can see this jump in about 3.8 million to about 4 million and something. So it takes about 486 days, which I mean that's like what, a year and a half maybe, to hypothetically wipe out Liberia, or to infect Liberia. All right. And then they do the same thing with Earth being 7 billion people. So then you kind of drag down the data again, and we get to a point where between like 719 and 720, there's a jump from 6.9 billion to 7 billion. So about 719 to 720. So then they ask, like, what can we do about spreading disease? So I think this might have been made during COVID. I don't know. What would you do to stop spreads of disease, right? Wear a mask, wash your hands, quarantine, whatever. All right. Let's look at data set number 2. It's a pretty boring lab. No, it's exciting. It's not boring, but I think I could have done this in 10 minutes of stuff. Sorry for dragging this out here. All right. Is this 2? Oh, this is 2. I think this is 2. All right. Number 2. They really don't give you much explanation here, but let's just talk about what I did here. You open the data set 2, you highlight all this data here, and before I was highlighting A and B like this, so dragging across A and B at the top and then inserting a scatter plot, and I realized there's a difference because in the lab here they say around t equals 200 there's a jump in the data, and time 200 did not show up on my graph, like on the x-axis here, so there's no 200, but then I look at the values, there's definitely a 200 on the left side here. It's 200. So I was like, why did that happen? And I realized instead of highlighting A and B like that, it helped to just highlight the data like this, and when I did that, I was able to actually see the 200 on the graph here. So that's where I got the one I have at the top here. Anyway, so we have this data, and what do they ask about it? They say does it still follow an exponential growth? And what's going on with the concavity of it? So it kind of has that exponential growth, right? And it's concaving up, but then there is that jump, and then all of a sudden it's like it's kind of concaving, starting to concave down a little bit. So it's almost like it's ramping up, and then it might be starting to level off, right? And they say, so the jump at 200, why do you think the jump might have happened? I don't know, maybe there's a crazy, just like, spike in the numbers there. I don't know why that would have happened. I'm not an expert, but yeah, I don't know. I would say just there's some crazy super spreader or something. So anyway, they go from talking about the exponential differential equations to logistic growth models, where logistic growth is where, like, you know, something might be growing over time, but then it starts to level off at a certain value. So you can kind of see they give us the general equations here that you might use, and they actually fit a function to the data that we can see on the right here, right? And this is a logistic growth model. So they say now use this function to determine what this revised model predicts as t goes to infinity. So here's the important part. Again, I don't think they like explicitly ask you to do the whole column with t values and n5 here, but I did it anyway to kind of, you know, understand the data here. So we do t values. I just did like 0 to a few hundred, like 300 or 400, whatever, and then input the function that they give you. Let's do the side by side. Looking up here, here's the function, here's this function. You can see everything here. All right, hit enter, and we drag this down. And basically they're asking, as the t values get infinitely large, what's happening to the n values? So we scroll down, looking at this column here, right? Getting larger and larger and larger and larger and larger and larger. And they're sitting at 78, 7,900, going up, going up, going up, going up, going up. And you see they start to just, you know, kind of level off around 70, you know, just about 8,000, right? So that's the idea. So user function to determine what this model predicts as t goes to infinity. It's predicting that it's going to infect just up to 8,000 people, and that's it. They're going to hope to, I guess, stop it around 8,000 people. So do you think their measures were successful? So I don't know. I mean, it looks like it's leveling off based on this, you know, predicted data and this predicted curve here. So, I mean, hopefully, yeah, you would hope they are successful eventually. I don't know. Kind of weird questions in this lab. I don't know what's going on, but we're going to go to lab 3 here. Or not lab 3, the, you know, data set 3. And they give us just this brief little whatever. So the Ebola epidemic was very real, and many people died. And fortunately, they were able to curb the disease's spread, ending the epidemic as 2015 came to a close. They say, you know, open lab data set 3 to see the complete data set. How closely did your prediction match up with what actually happened? I think they're talking about the prediction of 8,000, or maybe the prediction of whether their measures were successful. I don't know. But what I did is just graph the data here. So highlighted all these columns and got a little graph. Let's make this a little bigger. So over time, you can see there was that jump still, but then, I mean, it killed off right at, in this case, about 10.6 thousand. Yeah, so you could also look at the data here, right? 10.6 thousand was like the leveling off point. And so, yeah, that's pretty much it. So how closely did your prediction match up? I mean, 8,000, kind of close to 10,000, 10,600. It could have been better. How might you improve the accuracy of your model? When they say your model, I don't know what they mean. Maybe they mean this model here. Maybe just change this 8,000 to a 10,000, 10,600. I don't know. Kind of whack questions, but let's wrap it up here. The biggest takeaways are this. If you have a rate of change that is a constant times n, You could say it's like the rate of change is proportional to the, in this case, the rate of change of the number of people infected is proportional to the number of people that are infected. That differential equation leads to a exponential growth function or curve, right? And then in the situation where was the stuff about logistic growth? I'm skipping over it. There it is. And then in this situation, if you have, I don't even know how you describe this. It's like the rate of change is, it's still changing like based on the number of people, but there's also like a limit, this L value, there's a leveling off point, right? Then you get this sort of logistic growth function, which kind of has this behavior more. So yeah, sorry, it's kind of a rough lab. I hope you took something away from it. But for these goals, practice building our own models, exploring the impact of constants on models, the different A and C values, predicting outcomes of a disease based on rate of spread of a disease, and determining the accuracy of the model based on the real-world data. I guess we technically kind of did that. It's a little rough around the edges, but again, I hope you learned something from this. Hope this helps. Maybe, maybe not. If you have questions, let me know. Do the best you can. Yeah, all right. Bye-bye. I'm going to hop off this.